Okay, so why don't we start? Well, good afternoon or good morning, everybody, depending on where you are. Welcome to the second talk of our first cycle of talks at University of Porto. This is dedicated to quantum computing. And today is my great pleasure to introduce Dr. Federico Spedalieri, who obtained his degree of Licenciado in Ciencias Físicas from the University of Buenos Aires, Argentina, in 1994, and its PhD in physics from the California Institute of Technology in 2003. He worked as a postdoctoral scholar at the Jet Propulsion Laboratory in Pasadena and at the W department at the University of California, Los Angeles. He's currently a research assistant professor in the Ming-Hsieh Department of Electrical and Computing Engineering and a research lead at the Information Sciences Institute of the University of Southern California. Dr. Spedalieri works on several aspects of quantum information, such as bridging the gap between the adiabatic computing model and applications to many different fields: machine learning, scheduling and planning, circuit fault diagnosis, among others. He's interested in quantum sensing that aims at characterizing the ultimate limits imposed by quantum mechanics on practical sensing. So thank you again, Dr. Spedalieri, to join us, especially because you are in Southern California and it's now 8:30 in the morning. For some of us, I know how hard it is. So take it away. Thank you.
Okay. Thank you, Pedro, and everybody for the invitation. And well, I hope I do a good job of trying to give you an overview of some ideas in quantum computing. And in particular, I'm going to delve a little bit into what quantum annealing is and what are the challenges that we're facing. So let me start by kind of situating ourselves a little bit. So what is quantum computing? And essentially, we want to apply the laws of quantum mechanics to the processing of information. That's essentially the goal. So what quantum computing is not, and I always like to stress this, is not a magic thing, right? So anything a quantum computer can do can be done by a classical computer and vice versa, just because you can simulate a quantum computer, right? So why all the fuss? Well, the problem is that, yeah, that simulation that you can do, it's not necessarily efficient. So that's was actually one of the motivations for thinking about quantum computing. So there is then the possibility, and there are some examples in which quantum computing can solve certain problems that seem very hard for classical computers more efficiently. So, and that's something that you are very aware that is very important to investigate. So the main question, I guess, is quantum computer more powerful than classical computing? Well, we don't know. We don't have a proof one way or the other so far. So we have some tantalizing examples, like we're going to mention the Shor's algorithm for factoring large integers, that it has an efficient implementation in a quantum computer, but we don't know if it's actually a hard problem for a classical computer. And then other problems that we know are hard or classified as intractable for classical computers, we really don't know if the quantum approaches we have will produce an exponential speedup that will change the type of complexity. We have some interesting speedups that are polynomial that may not be as exciting, but in practice, they could be very useful, like in the case of the Grover search of searching an unstructured database. So the main thing is that this is still open, trying to figure out whether quantum computer is more powerful, but it's likely that it's going to have some niche applications in which you're going to get some advantages. May not be exponential, but will be things that will allow you to do certain computations that will be very hard to do with classical computers today. So the main thing is that this is still open, trying to figure out whether quantum computer is more powerful, but it's likely that it's going to have some niche applications in which. Well, I mean, we know that there are certain things like searching an unstructured database that you can get a polynomial speedup, a quadratic speedup with a quantum computer. So that's an advantage, but in terms of the complexity classes in computer science, doesn't change anything. But there will be certain other applications that likely will have, again, some gains that may be polynomial. And those will be very useful in practice, even if we don't change the computational complexity of the problem, for example. So as I said, the idea of quantum computing is to apply quantum mechanical laws to processing information. And also, what is this quantum mechanics? So it's one of the triumphs in 20th century physics, together with our understanding of relativity and the universe at large scales. So it explains the behavior of subatomic particles. That was the main motivation. And one of the defining features that it's highly counterintuitive. So some of the defining features of quantum mechanics. One is the quantum superposition. So classically, if you have some physical system, it may be in one state A or a state B, and maybe you don't know it, but you know that it's in one of them with maybe some probability, and that's your best description of the system. But a quantum mechanical system is allowed to be in another state that is defined as the superposition, that is some sort of intermediate state that doesn't have an analog in the classical world. And the most famous example of that is this idea of the Schredinger cats experiment, in which you put a cat in a box with a pile of poison that is can be broken by a hammer, that is triggered by the decaying of unstable nucleus, right? And because that decay is described quantum mechanically, the state of the atom is actually in a superposition of having decay and not having decay. But if it decays, it breaks, makes the poison vial break, and then the cat is dead. But if it doesn't decay, nothing happens, and the cat is alive. And the natural conclusion in the description of this problem quantum mechanically is that the state of the cat is somehow something that is not dead or alive, but is some weird superposition of both states, which is hard to kind of wrap your mind around if you're used to classical systems. The other feature is that we have these weird superpositions that we can create that seem to be very exciting and interesting. Gives you new physics and potentially new uses. But every time that you want to see what's going on in a quantum system, the measurement, the act of looking essentially, or making it interact with the detector, will destroy these superpositions. So you're only going to get some partial information about what's going on. So you will get, instead of seeing that the state was A plus B, like this weird superposition, you're going to see states A or B with certain probabilities. And that also leads to another weird concept in quantum mechanics, which is the concept of entanglement. And I'm not going to go into like a lot of the technical details of what it is, but it turns out that it tells you that you can have in quantum systems, the correlations can be stronger than classical correlations. And you can have, for example, the most complete knowledge possible of a whole system, the most complete knowledge allowed for by the theory of quantum mechanics, without knowing anything about its parts. If you want to look at each part of the system, essentially your best description is that it's completely random. But the whole system, you know exactly what state it is. So that's one of the reasons that I said it's kind of it's counterintuitive. So what is quantum mechanics so great? Well, it's been incredibly successful. It's the basis of our understanding of interactions with matter, electromagnetic fields. All of this are based on quantum mechanics, and if you want to go to the details, so it underlines our modern technology. So electronics and the understanding how transistors work has to do with understanding the quantum mechanical behavior of electrons in materials. And another things that are basically important research subjects is that many interesting properties that can have really a big impact in our society, like, for example, having high efficiency solar cells or high temperature superconductors, the behavior of those materials is, to understand them, we need to understand the quantum mechanical behavior. And the problem is that doing that is very hard for large systems. But I'm trying to motivate what got people to thinking about quantum computer. So I hope you can see that, well, understanding these materials can have a lot of impacts in technology, and basically in the same way that electronics and, for example, the information age changed the way society works. And you can trace back that to understanding these interactions in quantum mechanics with different materials. So what is missing to go forward to like exploit quantum mechanics to even change the world in a bigger way is that many of these phenomena, like for example, electrical properties and superconductivity of materials, emerge when a large number of particles are involved. And the problem is when we try to simulate a system with a large number of particles, the problem becomes really hard pretty fast. So the resources that you need scale exponentially with the number of particles. So imagine that you want to kind of understand what happens in a transistor or in a particular material structure to understand if there is some superconductivity phase. You're talking about like 10 to the let's say 10 to the 23 electrons working together to give you like the size of like Avogadro's number to give an idea of how many particles are going to work together. And simulating that from a first principles perspective will mean that you need a space of the size that is exponentially the number of electrons. So as you can see, these problems will become very complicated very fast. So we know how to solve the hydrogen atom because we have one electron. The helium atom, then we don't know how to solve exactly. We can simulate some things, but then if you go to larger atoms where you have more and more electrons and you need a bigger space, that's a whole area of molecular physics and atomic physics trying to understand that, because it's hard to simulate. So around the 1980s, Richard Feynman's insight, he was kind of thinking about these problems of simulating these material properties and quantum systems. And basically, he thought, well, for us, it's very hard to simulate the systems by writing like classical, like differential equations and running on a classical computer. But nature seems to kind of simulate itself very efficiently, right? So probably nature is using something that is better suited to simulate quantum systems. And because nature is quantum, we should try to do the same thing. Use a quantum system to simulate some other quantum system, and then try to find the answers to some of these problems that characterize this material. So that was an interesting idea, and people were thinking different ways of trying, how would you do that, and so on. But I guess, there was some mild interest until 1994 when Peter Shor showed that if you had one of these quantum computers, then you can take the problem of factoring large integers and solve it more efficiently. So solve it in polynomial time. And since the best known algorithm for that classically is exponential, and this problem is at the root of many cryptographic applications, like suddenly everybody was interested in these new quantum computers, this new idea, because they were solving a problem that could have practical applications beyond just simulating quantum systems. So around that time, the interest in quantum computing exploded. So let me go a little bit to more technical details to try to give you a flavor of what is thinking in terms of quantum computers. As we said before, that the application, quantum computing is the application of the laws of quantum mechanics to information processing. So what are these laws of quantum mechanics? So I'm going to mention like the main things that to give you an idea of how these computers work. First, the states of your system are represented by vectors in a Hilbert space. So because it's a Hilbert space, a vector space, you have not just the concept of a state, but you have a definition of the concept of adding two states, right? Like you have the concept of adding two vectors. That leads immediately to this concept of superposition. So you can have two states that, again, could be related to classical states of the system. So for example, in a transistor, it could be on or off, and that's a classical description of the transistor. But if we represent that quantum mechanically, naturally, we are allowed to have another state which is just the sum of the vectors representing those two alternatives, and that will give us a superposition. The other feature is that the evolution of a system in quantum mechanics is represented by a linear unitary transformation on this Hilbert space. And that leads to one of the features of quantum computing, which is this sort of parallelism where you can apply the same transformation, not just to one input of your system, but a superposition of the inputs of the system. And because of the linearity, is the same as then getting the superposition of the outputs of the computation. And then the last important feature is that measurement. So every time that you want to look at what the computer did, those superpositions are destroyed. So when we go to the details, so let's look at the quantum states and qubits. So you're familiar in classical computer science, we have the basic unit, the classical bit. The states are 0 and 1. And basically you operate on collections of bits following rules, and that's how computers do all the calculations that they do. If we go to a quantum computer, then we replace the 0 by some state in the system that we're going to note with this funky notation called the Dirac notation. And that represents one state of the physical system, but also you can think this is one vector in a Hilbert space that we use to represent physical quantum systems. So then the other state 1 becomes another vector that in this Hilbert space, they are orthogonal to each other. So they form a basis of all the possible states of a single bit, of a single quantum bit or qubit. But the difference now is that we are allowed to have states that we call this superposition. So we take any linear combination of these 0 and 1 states. And these alpha and beta are complex coefficients that need to, whose magnitude sum to 1. Actually, the magnitude square is related to the probability of seeing each one of those states when you look at the machine and destroy the superposition. But in principle, I mean, these are complex numbers, and this is the representation for one qubit, but you can imagine if you have many qubits, you're going to have a similar linear superposition of all the possible states of this bit. So what is this idea of the parallelism that the unitary evolution and superposition give you? So classically, so this is a very simplified way of putting things, but in classical computers, you have some algorithm that takes an input, gives you an output. Well, you have to send, if you want to compute it for several inputs, well, you have to send the inputs one by one, compute it, and you get the function of the input, that's your output. For a quantum device, you're allowed to generate superpositions of all the possible inputs, for example, or a subset of them. And then you apply the computation, which, as I said before, is just a unitary transformation in that space. And the unitary transformation is a linear transformation. So I can apply it, I can essentially, the mathematical form is that it goes inside the sum, and then it's applied to each one of the terms in the sum. So basically, applying the transformation, the unitary transformation to the superposition of inputs will give you a superposition of all the outputs. So the first thing you can think is like, oh, that's great. I mean, I can compute many things, and in one go, I have all the answers. But the catch here is that this feature that measurement destroys superposition. So basically, it's like you have this device that computes all the answers at once, but only shows you one at a time every time you look. So you may think, well, I mean, that seems like a wash. So it seemed that I had an advantage, but it's not there. Well, but then comes the art, I guess, of trying to exploit this. And there are certain situations in which you're not looking for the value, for example, of the function or your computation and all the inputs, but you're looking for some global property of that function. So the typical example is, let's say that you have a function that is periodic and you want to find the period, and you don't know exactly the structure of the function, but you can compute the function for a given input. So classically, you will need to send inputs until you find two of them that have the same value, and that will give you like a multiple of the period. But quantum mechanically, you actually can do this in superposition. So send all the inputs at once, compute the superposition of all the outputs, and then apply what is the equivalent of a Fourier transformation that in quantum, with a quantum computer, the quantum Fourier transformation can be done efficiently. So it scales polynomially. And this is opposed to like even the fast Fourier transform is exponential in the number of, on the dimension of your data. So for example, you can use a quantum computer to find the period of some function in polynomial time. And actually that is exactly the key element in Shor's algorithm. So Shor's algorithm reduces the problem of finding the factors of a large integer by using some number theory results to finding the period of a specific function defined as a modular equation. And because you can do the quantum Fourier transform in polynomial time, you can find that period and then use that to construct the factors of the large integer. So in some sense, the superposition, even though it looks like it's not useful because when you look at it, you destroy it, it can allow you to do operations on the inputs. And maybe if what you're looking is not exactly the value of the function of each input, but some global property, you may still be able to extract that global property without ever knowing the value of the function at any point. And that seems to be the key in many algorithms, quantum algorithms that seem to have an advantage over classical ones, is when classically you're not, essentially it's unavoidable to do certain intermediate steps and compute things that are not are not the answer that you're looking for, but you need to construct the answer that you want. Like in the case of the period of a function, finding the value of the function for each input. But quantum mechanically, you do that in superposition. That information is there, but it's not accessible to you. Or if you try to access it, you only see part of it. But you can still operate on it and extract the global property without knowing the details of the function for each input. And then many quantum algorithms that seem to have an advantage have this sort of feature that you can do computations, intermediate steps that classically you cannot avoid. But in the quantum superposition, you do them in a way that you are not allowed to know. You cannot see them, but you can see the results of a certain global property that they have. So, okay, why don't we have quantum computers? Well, the problem with building these devices is that they're extremely sensitive to noise. Quantum information, if you have these nice superpositions that give you the power of this information processing, If you have interactions with an environment that are uncontrolled, those destroy the superpositions, and essentially your system becomes some probabilistic mixture of different states. So it loses that new element of the quantum superposition. So, well, let's try to have computers that are not that noisy. Well, you need to build the components that have very high reliability. And that's something that it's also not easy to do. And people have been working on this for several decades, and they're inching up in terms of the reliability of these devices, but we still not there in terms of what we need. There is an interesting and a very powerful result that says that we can deal with errors. So if you have these unwanted interactions that affect our quantum state, we have techniques to deal with them that essentially is quantum error correction. But the problem is that they require a very large overhead to implement. It's still a polynomial overhead, but in practice is very large. So to give you an idea, this may not be the most up-to-date numbers, but if you want to simulate the system with 100 qubits, you may need millions of physical qubits to perform all the error correction that is required. And I want to point out that quantum error correction is a completely different animal from classical error correction because of one other property of quantum information. That is, quantum information cannot be cloned, cannot be copied. So for classical information, one of the simplest way of dealing with errors is to just copy the information and do majority voting if one of them is flipped by an error. Quantum mechanically, you cannot copy an unknown quantum state because essentially to know what the state is, you need to measure somehow. And when you measure, if the state was in a superposition, you destroy the superposition, so you didn't learn anything. But there are ways of correcting errors without knowing what the state that was corrected is. So there are techniques that have been developed there, and there's a very important result that says if the error rate that we get, like per gate or per transformation, is below a certain threshold, then there are these techniques that you can apply, and then you can carry out the quantum computation for as long as you want. So that's the fault-tolerant threshold theorem. But again, we're still not there in terms of the different error correcting codes have different values of the threshold. Some of them, the threshold is very small, so you need very high reliability in your components. So people are working to devise new error correcting codes that have higher thresholds. And on the other side, people are trying to build components with the highest reliability possible so you can match the two of them. But even when you match the two of them, you know what to do, but you still need to build a very large overhead to implement those transformations. So it's still a practical challenge to get there. So let me give you the flavor of quantum computing and what we call the different models of quantum computing, because you may read certain papers or results and some of them may seem that they're doing different things. And the issue is that there are different ways of doing this quantum computation. In some sense, the best way to understand why these models that I'm going to discuss in a minute are the same is to think of computation as a state preparation problem. So you have some description of your problem, and you want to find, and you have a system on which you're going to do transformations. Could be like the register of a classical computer or the register of a quantum computer. And your program, your algorithm is, well, you just want to create a state that when you look at it, when you measure it, it has the information about the solution of the problem that you're looking at. So if you're solving satisfiability, you're going to do certain transformations, and at the end, you want to see a state that you can, from that, extract the satisfying assignment of your satisfiability problem. So when you look at that, I mean, then it will become clear why these models are kind of, why in the end they have the same power. So let me start with the circuit model, which is something that is the most natural that you can think of in terms of, given that we are very familiar with electronics and classical electronics. I mean, you do logic by applying gates to bits and changing the states of the bits depending on other bits and combining them like that. And the circuit model essentially will take that idea and you replace the bits by qubits. So now your registers are these quantum systems that can have superpositions. And you're going to have a different set of gates because these gates are going to be unitary transformations in those spaces that will allow you to generate the superpositions. But essentially what you're doing is the same idea that you do with a classical computer. You have a register and you start applying like logical gates to the information in the registers in a particular sequence that represents your program in order to end up in a state that has the answer to the problem that you're trying to solve. The difference here again is that the registers are quantum bits and the gates are quantum gates that perform transformations in this Hilbert space of the quantum system. But in the end, you prepare some state and then you're going to measure, you're going to destroy some superpositions, but the algorithms maybe that can be constructed such that that measurement will allow you to extract the information that you were looking for example, the period of the function that I mentioned before. So this is sort of like the model that people usually are more familiar or have seen articles discussing this approach. There's another way of doing quantum computer, which is called the measurement-based quantum computing. And the idea now is that you're going to have a very a general, what is called kind of a cluster state, which is a particular state of many qubits, that it's always the same state. You start with that state, and in particular, it has the property that is a highly entangled state, so it has these quantum correlations. And then the way that you apply that essentially you're going to generate the state that has the answer to your problem or apply your quantum code if you want. Instead of applying like gates that transform several qubits at the same time, depending on the state of another qubit and so on, this is carried mostly by measurements. You measure a qubit in a particular sequence, and depending on the state, on the outcome of that measurement, you're going to apply one transformation to some other qubit next to it. And it will be like what is called a one qubit transformation. So you don't need to have two qubits interact. The entanglement that exists in this starting cluster state, it's going to propagate the information in a way that you're going to be doing a computation in which the states of different qubits are actually interacting. But you don't have to do it directly, and that has a very useful effect in implementations, for example, because in many cases, implementing a gate between two qubits, it's hard, technologically can be very demanding. So this implementation allows you to generate one single state that you can use for any computation, and then the sequence of measurements that you apply, and the measurements are for single qubits, will allow you to perform your computation. And then the last model, which is one that we're going to discuss a little bit in more detail, is the adiabatic quantum computing model. And this seems a little bit different from the other ones, but one thing that I want to stress is that all these models have been shown to have the same power. So anything that you can do in one, you can do in the others with polynomial overhead. So basically, which one you choose depends on, well, you're thinking about implementing this in some system. So Some of them may have advantages for certain systems and disadvantages for others. So that may guide which one of these you're going to try to use. So the adiabatic model, it's based on one feature of quantum mechanics, one result, the Adiabatic Theorem, that essentially says if you have a quantum system that is defined by a Hamiltonian that essentially is kind of like an energy function, and you have the system in the ground state of that energy function, so in the lowest energy state, and you slowly change the parameters that define that Hamiltonian, the state is, and you do that slow enough, then the state is guaranteed to remain in the ground state of the Hamiltonian as you change the parameters. So the idea of adiabatic quantum computing is saying, okay, I'm going to show it in the next slide again, but you know that you can solve certain problems, particular combinatorial optimization problems, as optimizations over discrete or binary spaces, right? So you can encode, construct an energy function such that the lowest energy of that function represents the solution of a particular problem. So what the adiabatic quantum computing will do is to first start in a state that is easy to prepare, and then slowly change the parameters to transform that Hamiltonian into the Hamiltonian that encodes the solution. And then you can look at the solution and you're guaranteed to have the lowest energy for that energy function. So let me, I guess, pick it up a little bit. So this is things that, well, as I mentioned, is probably familiar to you. This is the Ising model. It's a particular binary or discrete energy function of a system that you can use to encode essentially any combinatorial optimization problem. It was shown to be MP-hard in 1982. And the idea of adiabatic quantum computing is to replace this energy by the corresponding operators that operate on the space of the quantum system. And they look like this. This is done by Farhi in 2000. And then by changing the parameters low enough, you can start the system in at time t0. For example, this function b is 0 and the function a is 1 or high. And then the ground state of the first term, if you want, is very easy to prepare. It means that all the systems, the two-dimensional systems, have one particular state. And if you relate this to magnetic systems, it means that they're pointing in the same direction. In the transversal direction, in the x direction. And then the Ising model, the Ising Hamiltonian, represents the function on the top, has an energy function, and now the states will be the magnets pointing in the z direction. So in this context, solving a problem or programming a problem to solve with an adiabatic quantum computer means finding the appropriate values of these hi and jij. So these local biases and interactions between these elements, which are represented by qubits. So let me give you kind of like a flavor of what is it that you're doing, and in terms of classical annealing versus what is called quantum annealing. So this process of the adiabatic quantum computing sometimes is also called quantum annealing, in particular when you're considering that you're dealing with a system that it's in interaction with an environment, so it's more noisy. And the idea is that it will function like a classical annealer, but it will have also certain quantum features that will allow it, for example, to tunnel through energy barriers. So for example, in a classical annealing, you have an objective function with local minima, but you're trying to find the global minima that it's marked with the star. But depending where you start in your process, you follow the energy landscape down, and you may get trapped in local minima. So in quantum annealing, the idea is that we're going to start with some Hamiltonian for which the landscape looks like this. It's very easy. There's one optimum that is a global optimum, and it's very easy to prepare. And here on the left, I put the representations. If these qubits are essentially little magnets, it will mean like aligning all the magnets in the X direction by applying a strong magnetic field, for example. And then the idea is that we start changing the Hamiltonian a little bit. But if we do it slow enough, we know that the quantum state will always remain in the ground state of the instantaneous Hamiltonian. And then the idea is that we're going to transform this easy energy landscape into this hard energy landscape. But if we do it slow enough, we're guaranteed to remain always on the ground state of all this landscape. And at the end, we just look at the system, and in particular, it's looking at the state of each qubit. And now the state of each qubit, since they encode the solution to this classical problem, they're either up or down. And then you can read that out, and that's the configuration that minimizes the energy that, for example, encodes some combinatorial optimization problem. So, and this you're probably very familiar that combinatorial optimization is very hard. It's classically intractable. It's related to all these ideas of NP hardness, and you have applications like pretty much everywhere. So this is one of the problems that this adiabatic quantum computing seems to be well suited for, because it's easier to represent, or it's more natural to represent these problems as optimization of some discrete function, and that natural translates into designing a system that has that function as the energy that determines the evolution of the system. So let me discuss a little bit about one of the devices that is out there that actually follows this model and was one of the first devices to be commercially available. So the D-Wave processor, basically, they implement this idea of interacting qubits, or that you can think of it magnetic elements, and the implementation is on a superconducting, using superconducting technology. So essentially, you can represent these little magnets by the superconducting current on small loops. And then you have some other circuitry that you can use to control interactions between them, bias them, and so on. And all this can be done in the quantum regime. So the idea is to exploit the quantum effects of these interactions to be able to apply this idea that I mentioned before. We start with the system in a state that is very easy to prepare, because the landscape, it has only one minima, and naturally, if you cool it down, it will go to that state. And actually, these systems work at millikelvin temperature, so they're very, very low temperature. And this device has been shown to have the different quantum effects that you expect to be useful in this, like single qubit tunnel, multi-qubit tunneling, and they can generate entanglement between qubits. So that's all good. So basically, okay, let's solve problems with a quantum annealer. So we have one, the D-Wave processor. It has quantum effects. So, well, let's just pick a problem and solve it. So the problem starts when you go down to these details and you realize, I mean, the clash between like theory and the real world. So as an example, you have a graph coloring problem, and you're probably familiar with this. You can represent this problem. You can encode it as some cost function, and you're trying to find the optimum of this cost function, and the variables represent the assignments of colors to the different vertices in the graph. And you have penalty terms that tells you that you cannot have, that each vertex can have only one color, and then you penalize also two vertices that are connected and have the same color. So as you can see, this is a quadratic function on the variables x. So it seems like a good candidate to represent as the interactions between these little magnets that the D-Wave processor kind of does. Well, the problems that you start running into is that, well, first the size. So right now, the D-Wave system started with the first commercial one with 100 qubits. Now they're up to like 5,000 qubits. But that's, I mean, a pretty decent size of system, but you still sometimes have problems that are bigger than that. And the first thing that you're faced with is that your problem doesn't fit in the device because maybe it's too big. So first you need to design some strategies to decompose the problem or solve smaller problems. Another limitation that is pretty big is the fact that this system have very restricted connectivity. So in your problem, you map, let's say, a graph coloring to an energy function. And when you look at that energy function, because of all the terms of the penalties that you're using, you may need to have different, like all the variables interact with one another because they can influence their values. But when you want to map it to the system, you realize that, well, you don't have that control element that will allow you to tune that particular interaction. So your problem doesn't fit natively in the device. So you need to, there are some techniques of trying to make it fit. And usually what you do is you pay the price in using several qubits to represent a single variable. So you end up representing a smaller problem than the number of qubits that you have. Another issue is that this physical system has a limited parameter range and precision, but your problem is defined by whatever size. Your problem, the coefficients in your problem can have, in principle, any value. And if you have your parameters are limited, you can always try to rescale the problem to make the parameters fit, but then you're hit with the side of the precision on the other side. So if your parameters, in order to represent your problem, once you scale it down, you need like 8-bit precision, but you only have 5-bit precision, then you're essentially mashing different instances of the problem together. And that's a problem because you cannot trust on the solutions that you're going to get, or you're not guaranteed to get the right solution. Then you have, this is a real system, intrinsic control errors. You're trying to program HI and JIJ, but these are, in the end, are electrical signals that you send to the device, and then they're converted with digital to analog converters and so on. And there are errors that happen there, and you may be misspecifying your problem, and that will have another layer of issues to deal with. And then the last that is like for all implementations of quantum computing is that, well, your system is not going to be a perfect system. It's a system in the real world. It interacts with an environment, and there's noise. And noise is the enemy of the quantum superposition. So you may have everything that is great, but if your system is too noisy, essentially what you end up having is a very expensive classical system, because your superpositions are destroyed and you cannot exploit any of the quantum effects. So right now, let me give you and then you're probably aware, you've been reading articles about this. So there are several companies that are working on developing these devices. So D-Wave was one of the first ones to try to build something, and they started more than 20 years ago. But now you have IBM. They have a system that people can access and try it. You have Google that recently, about a couple of years ago, I guess, they came up with this interesting result. It's called quantum supremacy. You have Intel that the last time I heard, they're still working on it, but it's not that they have a device ready yet at the level of others, but there's active investigation there. And there may be others that I'm not listing here that could be smaller. There are actually several startups, Rigetti Computing and others that are looking at different implementations of quantum devices. So these devices are still small, but they're growing. The Google device up to about 50 or 60 qubits. D-Wave is in a different, the Google device is in the circuit model. The D-Wave is in the adiabatic model. It's bigger, but it's not easy to compare the two in terms of capabilities because they're computing in a different way. The IBM also, it's of the order, I believe, of 50 qubits. But they're slowly growing. But the problem is that because they're still small and we cannot really implement all the error correction that we know will take us to the promised land of fault-tolerant quantum computing, where we can compute anything. It's not clear that these devices will provide an advantage. So we know that they have quantum effects, but the question is, are those quantum effects there enough to improve computations at this scale? That's pretty much like the question at the frontier of research today. That's what everybody's trying to do. And for example, the Google result, the quantum supremacy, was to show that their device, they created a specific problem, which was sampling from the output of a quantum circuit, that they could construct the quantum circuit with their qubits and sample from it. And they argue that doing the same thing on a classical computer, which essentially will mean to kind of try to simulate the circuit, it was out of the question. So it will take years to do that. Of course, other people say, well, wait a minute, it will take years in the algorithms that you use. We have different ways of approximating this. And of course, it becomes the arms race of trying to simulate this better. And I think that's good, because that pushes everything, better simulations and better devices. But the key point is that that result is for an artificial problem. So even if, I mean, you believe that, yeah, it's doing something faster than you can do with a classical computer, well, it's not a problem that you will be interested in solving anyway. So if you want the advantage is it's interesting in the sense that now you have a device that is doing things that you cannot simulate. But I mean, you could think of that like any system that does some kind of like fluid dynamic simulation could be also comparable in that sense. But it's still not something that will give you quantum advantage on a problem of practical interest. So let me summarize. So as I said, so quantum computing is trying to use this laws of quantum mechanics and these very counterintuitive and weird features of quantum mechanics to exploit, to process information in a more efficient way. And the main issue of why we don't have these machines yet is because this quantum information is very fragile, and we need to have very high reliability of components that we are not there yet technologically. And even when we have that, that will require a large overhead where we're gonna, like most of the qubits in your system will be dedicated to error correction, not to computing, for example. But I think, I mean, I've been in the field since 1995 or so. And at the beginning, there was a lot of excitement. Then because of Shor's algorithm, then it died down. And now I think the exciting part is that people are trying to build these devices without really knowing yet if they're going to be useful or not, which could be seen as something rather foolish or something that, well, this is the way that you learn what you can do with these devices and what are the challenges to building them. And if you don't try them, probably you're not going to ever do it, because if you wait until you have everything set up to build 2 million qubit machine, probably you'll wait forever. So in that sense, it's a very exciting time that we are learning new things. And I expect that hopefully, I mean, I'm an optimist that maybe in the next 5 years, we're going to start seeing certain niche applications in which these small devices can provide some advantage. Not necessarily something revolutionary, not an exponential advantage, but could be that you have another tool to solve certain problems. But that's pretty much the research question right now. Are these devices at these small scales able to provide practical advantages, even though that they can generate quantum effects and can have these results of the quantum supremacy that Google did. So, and with that, I'm going to finish. And yes, please, if you have any questions, go ahead.
Okay, thank you very much, Federico. I'm wondering if there's any questions from the audience. I was monitoring this, and so far there's no questions. Yeah, so there's a question here. In adiabatic computing, when mapping a large problem to a D-wave topology, what should we deal with the chain break issues, or how should we deal with the chain break issues?
Well, I mean, that's a very I don't think that anybody has a good answer to that, because the chain break issues essentially is what I mentioned before. If you have a problem that doesn't fit the connectivity of the device, then what you do is to say, well, I'm going to group like groups of qubits, and sometimes you do it in a chain, that I'm going to ask them to represent the state of one of the variables in the problem, right? And essentially that the effect that it has, that is because now I have this chain of qubits that is more connected to the other qubits, so I'm increasing the connectivity, the effective connectivity of the problem. But essentially you do that, and you're assuming, or you're hoping, that your chain will behave as a single qubit. And the way of doing it, so essentially you're going to associate the state of that variable to 0 when all the qubits are 0, and to 1 when all the qubits are 1. But the chain break problem happens with one of those qubits doesn't agree with the others, right? So, and the issue is, okay, what happens when you map your problem and you have this chain that should represent a single variable, but you measure and all the qubits in that chain, they're not have the same value. Some of them have a different value. So, I mean, one naive approach would be, well, it's a majority voting. But the thing is that majority voting doesn't guarantee that that will be the right choice, because the cost of breaking the chain, it doesn't have to do necessarily with the number of bits that you're changing, right? It's so you can imagine that so it can cost less to break the change with a lot of qubits, so to flip a lot of them than to flip a single one. And then since the system is just following the energy, it's going to produce like results that the whole system should have been 0, but it flips only one of them, or I mean, it flips a lot of them that will make it change to a 1, but because the energy is less than just flipping maybe a few in different places, and then you get a misidentification of what the actual value was. So the problem is that it's not a good, in my opinion, it's not a good like this minor embedding and the chains. I mean, you do it because you don't have all the choices, but it's not something that is really very solidly motivated by the physics of the device, and that will allow you to get correct answers. So in some sense, it's like any change that breaks, essentially the machine is saying, I cannot tell you the value of that, and it could be either one. So the fact that the majority of the qubits are in one direction or the other doesn't really reflect their effect on the energy. So you're reduced, let's say, if you're solving a problem with 100 variables and 20 of them are broken, well, essentially for those, you will need to search all the possible values of those 20 variables to see which one of those with the values that you got from the other ones are minimize the energy. For 20 may not be bad, but if you have
Federico, I think what you're essentially saying is that it's not you cannot trivially decompose a problem in this model, or the way you decompose it has to be such that you now rather than decomposing in 2 problems, you have to decompose in more problems that overlap, so to speak, right?
Yeah, but it's not as much as decomposing as like mapping a problem that has more connectivity than the device natively allows you to have. And either, I mean, when you're faced with that situation, you're either change your problem by dropping some of the connections, or what you do is like, okay, you map one variable to more than one qubit, and then you make those qubits interact strongly to force them to be all the same. But when they break, it's not necessarily that if only one of them broke, it means that then, okay, the one that is wrong, I forget about it and I do majority voting on the others, because that's the same energy. It takes the same energy to do that than to flip n-1 and leave 1 correct.
Yeah.
Because the energy of those things has to do with the difference between, the energy penalty when you have two qubits next to each other that have different values.
Okay, real quick, because we're really close to 1 hour here. So at the beginning, there was a lot of promise of the use of this technology for software V&V, verification and validation. I mean, what's the status on this? Are people using more the adiabatic model for that, or rather than the circuit model? Is there a specific quote unquote machine model that is more suited to that particular domain? What's your take on that?
I wouldn't say it was great promise. It was a great hope.
Okay, all right,
so,
fair enough.
I mean, it was, some people were motivated to say, well, it's a different system maybe, and this is a big problem. But I mean, the way that I remember it was trying to be implemented was first sort of mapping the problem to some sort of machine learning type of anomaly detection, and then trying to characterize the set of, let's say, code that is behaving and doing things correctly, and then you put some errors and try to learn somehow that the two spaces and then compare them. I don't believe that any of that really bore any fruit, and I'm not sure of people trying to do that in other implementation. I think, I mean, V&V is much even higher than any of the other problems of combinatorial optimization in terms of how hard it is to really get a handle on it.
Yeah, it seems to be a little bit more complex even than SAT and whatnot. Okay. There was here one last question about errors and error correction. In one slides, you mentioned you know how to deal with errors, but it consumes a significant overhead. Could you elaborate a little bit on this? And also, I'm wondering, what are the sources of errors here? Is just the reading errors, or is there some inherent error due to the entanglement of the beads, for instance?
So the errors could be reading errors. Essentially, your device, you want to measure something and you measure the wrong thing. Or more typically is that your system is interacting with an environment usually, and that means that the environment can kick your system and some of the qubits can be flipped from one state to another, or essentially the way that we represent, they apply extra unitary or extra transformations on your state. So you're doing the computing and it's like somebody comes once in a while and flips one of the bits, classically, but quantum mechanically, I mean, they do some kind of quantum transformation. And the problem, as I mentioned before, is that since we cannot copy quantum information, we cannot say, oh, let's do some majority voting, right? But there are ways of encoding the information, encoding a quantum state in a bigger Hilbert space, in a way that whenever you have an error, so you have an error model, so these are the possible errors that can occur. Whenever an error occurs, you can learn what error occurred, and you can undo it without ever knowing what the state of your system is. So there are ways of extracting the syndrome of the error, and basically tells you, oh, this happens, and then you apply the transformation that will undo that. But you can do all this without ever knowing what the actual state of your system is. But yeah, and basically you have to, you're gonna have different error correcting codes that are better for different error models. So it will work better for bit flip models or defacing models, or defacing errors and bit flip errors and so on. So it's, I mean, it's a whole field in quantum information, the quantum error correcting codes. I don't know if that kind of answers more or less the question. I mean, some codes are built with some ideas of classical codes, but you have to take into account the fact that any classical technique that requires you to know the value of the bit or the comparisons, it's not going to work directly.
Okay, all right. So let's wrap it up. Thank you very much, Federico, for this talk. And thank you for taking the time to be with us, especially getting up early in the morning in California and sharing this presentation. Thank you. Have a good one. Thank you very much. And everybody, just a reminder, next week, we're going to have